Okay, good afternoon, everyone. So I hope you are finalizing your problem set. The deadline for submission is tomorrow at 5 p.m. So upload nyo siya sa Canvas. So again, please give some time para sa uploading. So para sa contingency na biglang bumagal yung internet and so on. Huwag nyo antayin yung mag-upload ng 4:59. Especially you have to upload 4 separate files. So medyo time nga nyo ng konti. And then I'll try to finish grading everything hopefully by tomorrow. Pag sinipag ako tapos kong checkan lahat by tomorrow. If not, hopefully by Thursday, right before we start the class. Para if you have some common questions or some reklamos, pwede ko siyang i-address sa klase sa Thursday. But I'll try to finish everything, grading everything as soon as I can. Dun sa mga nag-submit, isa na lang yung hindi ko na-checkan. So I'll try to do that. And then by the way, hopefully matapos natin today yung coverage ng Unit 2. Or at least definitely by Thursday tapos natin siya. So that means we can push through with the problem set next week right before you go into the reading break. I guess that's a good time so that wala na kayo talagang iisipin during the reading break. And then also, sorry, medyo nagpatong-patong yung requirements natin. I already uploaded, ka-upload ko lang, mainit-init pa, mga 2 minutes ago, or di pala, mga 5 minutes ago, sa Canvas yung homework number 4. Um, the deadline of which would be on the November 29. Tandaan niyo ba guys kung kailan yung napag-agrihan natin na deadline ng problem set? Tama ba? Starting 27 hanggang November 1. Yan ba yung napag-agrihan natin na prob set 1? Prob set 2.
Sir, ang
Parang,
tanda ko lang po, sorry.
go ahead.
Ang tanda ko lang po ay sabi niyo po before yung reading break.
Okay, sagad din natin. Ang reading break ay November 2 yung start. So November 1, 11:59 p.m. para hindi ako makasuhan na nagpapagawa ng something during the reading break. So yun na lang yung deadline, November 1. Tapos kailan siguro natin ibibigay. So kung 4 items uli, so I'll give you 6 days to finish it. So 1, 2, 3, 4, 5, 6, November 27. Pero siguro pwede ko na siyang ibigay November 26 para meron kayong 2, 4, 6, 7 days including November 1 and Sunday para magawa. 4 items lang naman uli. Gusto niyo ba yung ganong setup na magbibigay ako ng 5 problems, pipili lang kayo ng 4? Or gusto niyo sasagutan niyo na lahat? Magbigay na lang ako ng 4, tapos sasagutan niyo lahat. Ano sa tingin niyo? Kasi tinatry niyo rin naman yung 5, di ba? So, I don't know if that helped or medyo nakapagpahirap pa ng konti. What do you think?
Sir, yung date po na nakalagay sa'yo is November. October pa lang po, sir.
Ay, oo nga, no? Sorry naman. So, yeah, thank you. Buti na lang sinabi mo, CK. So, yeah, October. Babaguhin ko yung naka-upload sa Canvas. Alright, so deadline ay October 29, no homework 4. Right? So siguro ganun ulit. Magbibigay ng 5 tanong, tapos pipili lang kayo ng 4 na isa-submit. You have 7 full days to finish it. Those holiday, November 1 and Sunday, October 31 will be covered. Pero at least that would be better than ipasubmit ko siya kagad ng November 29. Okay. I'll give it to you November 26 at 8 a.m. So deadline ulit ay November 1. But as usual, submit it as soon as you can. So para makapag-feedback ako kagad. And then homework 4, in-upload ko na siya. Ang deadline ay October 29, though I think I promised na yung deadline ng homework 4 ay before mag-start yung problem set 1. Pero probably if you want to work or to give more time to it, sige, gawin ko yung deadline October 29. Pero kung gusto niyo siyang tapusin before October 26, kung kailan mag-start yung problem set, then the better, right? Para hindi niyo na siya isipin. Isang problem lang naman, 4 points. You consider the sequence, this given sequence. And then 1 point ay parang kumustahan lang. Though medyo marami na kayong bonus points, so sinama ko na siya sa over. So 5/5 counted yung 1 dun sa denominator, dun sa problem number 2. So kindly answer that. So yeah. Para balance it, two homeworks for each of the two units. All right? So babaguhin ko na lang yung file dun sa Canvas, pero October 29 naman yung nakalagay na deadline dun lang sa hard file, dun sa PDF copy, November 29. Pero dapat October yun. Okay? And then, may utang pa pala ako dun sa top-notchers ng homework 4. Hindi ko pa nasa-summarize yung pa-shoutout sa kanila. I'll do that next meeting kasi nakalimutan ko siya kasi masyado akong na-excite pag-check ng problem sets nyo. Kalimutan ko siyang gawin. So next time na lang. And then quick recap of what we did last week. We talked about some important or some major theorems about sequences. Namely, we talked about the monotone convergence theorem from last time. Sinold natin yung problem natin na ano yung kulang sa pagiging bounded ng isang sequence para siya ay maging convergent. So sabi natin, dagdagan mo lang yan ng monotonicity, so automatic magiging convergent na. So MCT tells us that if you have a monotonic sequence that is bounded, then automatically it will be convergent. So others call the monotone convergence theorem as the monotone bounded convergence theorem para hindi nila makalimutan na kailangan bounded. Hindi sufficient yung pagiging monotone na, so dapat bounded yung sequence. Kasi yung sequence 1/n, 1/n, hindi pala 1/n. Yung sequence na n, right? It is increasing. So monotonic siya, pero hindi siya convergent. Ang problema niya, wala siyang boundedness, right? So in order to say that the sequence is convergent, one sufficient condition is to show that it is monotonic and convergent. And this is extremely helpful, especially if you don't care na malaman kung ano yung limit ng sequence. Kung gusto mo lang i-determine kung siya ay convergent or hindi, pwede kang gumamit ng MCT. Ipakita na siya ay monotonic or i-check kung siya ay monotonic, either increasing or decreasing, at saka bounded, then sufficient na yan para masabi na convergent yung sequence, right? Even without the knowledge of what the limit is. And then also, pwede niyong i-relax ng konti yung condition about monotonicity. Kasi di ba sabi natin, ang business naman natin when talking about convergence is what happens at the tail end of the sequence. Hindi importante yung unang 1,000, unang 1 million na terms dun sa sequence. Ang tinitingnan natin ay yung nandun sa padulo, nandun sa tail end, habang lumalaki yung subscript. So actually, merong isang weaker version yung MCT. I mean, weaker yung requirement. Hindi kailangan monotonic siya all throughout. Kailangan siya eventually monotonic. So kahit yung first few finite. Yung first finite terms ay kahit hindi sila monotonic, so kahit nag-oscillate siya, pero kung mapapakita nyo na sa dulo, eventually magiging monotonic siya, so pwede pa rin siyang pumasok dun sa monotonic convergence theorem. Basta bounded siya at eventually monotonic. Okay? So yun yung idea ng monotonic convergence theorem, and this is one of the big theorems that are equivalent to the completeness axiom, which we set to be the LUB property. Okay. Then aside from the MCT, we also proved the nested interval property. The nested interval property, pag meron kang mga interval, katulad nitong nasa picture, na nested, ibig sabihin, interval sa loob ng interval, na nasa loob ng interval, satisfying how many conditions are there? Una, dapat yung IN ay superset ng I sub n plus 1. Alright? And then dapat yung mga I sub n's ay non-empty. Then yung intersection ng lahat ng mga I sub n's ay non-empty. And if the sequence form by computing the lengths of each of the intervals converge to 0, then alam natin na yung intersection isa lang yung laman. At yung intersection in actually would be the limit of the lower bounds A sub n and the upper bounds B sub n. So again, if you will recall sa MBT, sa MCT, ang main ingredient ng proof ay LUB property. Tapos dun sa nested interval property, ang main ingredient ng proof ay MCT, right? Then actually it can be shown, I think, hindi ko sure kung madali, pero I think it can be shown that the MCT will the nested interval property will imply the LUB property. So parang magkakaroon tayo ng chain na LUB implies MCT, then MCT implies NIP, then NIP will imply the LUB property. So really, these three statements are equivalent to each other, meaning if we will replace the LUB property as our completeness axiom, then we will create the same brand of calculus. Parehas yung mga theorems na madiderive natin. Kasi halimbawa, gamitin ko ang completeness axiom yung NIP, kaya kong ma-prove mula doon yung LUB property, tapos kaya kong ma-prove using LUB property yung monotone convergence theorem, and everything else in the rest of Math 155 will follow too. So yun yung idea ng equivalencies ng mga axioms or ng statements. They can serve in place of one as an axiom in a logical discourse. All right. So today we'll try to consider or to discuss more major theorems. I think we'll have 2 to 4 on our plates today. So let's start. But before that, excuse me for a minute. All right, so thank you. I'm back. So let's continue and look at the next theorem, next big theorem in real analysis or in advanced calculus. Right. So this is the Bolzano Weierstrass theorem. May typo, lagyan nyo ng L yung kay Bolzano. This is actually named after I think 2 German mathematicians. Wait, tama nga ta. Yeah, so I think it's Bernard Bolzano and Carl Weierstrass. And this theorem says that every bounded sequence contains a convergent subsequence. All right. Now, on its face, mukhang hindi ganon ka-useful for us or when talking about convergence of a sequence, yung Bolzano-Weierstrass theorem. Kasi sabi niya, okay, kung bounded yung sequence, dapat meron siyang convergent subsequence. Alright? And sabi natin sa analysis, mas gusto nating i-discuss yung pagiging convergent ng isang sequence. Kaya lang pag meron kang subsequence ng isang sequence, pag nag-converge yung subsequence na yon, hindi ibig sabihin convergent na yung sequence, right? Because for instance, consider the sequence -1 to the power n. Meron tayong ma-define na dalawang convergent subsequences niya. The subsequence containing purely negative ones, and the other one is a subsequence consisting of purely ones. Both of them are convergent, all right? Kaya lang yung original sequence ay hindi nagko-converge. It will just oscillate between 1 and -1. Pero yung sequence of negative ones obviously will converge to -1, and the sequence of all ones will converge to 1. So the idea is convergence of subsequences is a hard criterion to use for convergence. Actually, kailangan mo ipakita na lahat ng subsequences ay nagko-converge sa isang sequence lamang o sa isang number lamang. All right? Kasi, but even then, we are not sure if the actual sequence will converge, right? Ang alam lang natin, divergence criterion, na kapag ka nakakita ka ng dalawang subsequences na nag-converge sa magkaibang number, then the given sequence is divergent. Okay? Kaya medyo, kung isipin nyo, parang at this point, wala pang masyadong gamit sa atin yung Bolzano Weierstrass. Kasi ang ginagaranti niya, kapag ka bounded yung sequence, katulad nitong sequence natin na to, kasi bounded yan ng -2 below and saka +2 above. So meron tayong makukuha na convergent subsequence. Pero on its face right now, we don't know what's the usefulness of having a convergent subsequence, right? But don't underestimate Bolzano-Weierstrass theorem. Sa math, nagkakaroon ng pangalan ng isang theorem either kapag sobrang gamit na gamit siya or very fundamental siya or medyo may controversy o may konting chismis about that particular theorem or the circumstances behind that theorem, right? Pero itong Bolzano Weierstrass, it is very important. Number one, it's equivalent to the completeness axiom. So meaning lahat ng napuprove natin using LUB property can be proven using Bolzano Weierstrass theorem. And then also Bolzano Weierstrass theorem can give birth to other known theorems like extreme value theorem. There's a version of the proof of the extreme value theorem that uses the Bolzano Weierstrass theorem. So for now, wala siyang utility for us, pero let's appreciate it for what it is, basically as an equivalent to the LUB property. Okay? Tapos you will see in the proof that we will rely on the nested interval property. Kaya mapapansin nyo merong hierarchy yung pagkaka-state ng mga theorems, yung mga big theorems dito sa unit na to. Kasi parang chain yan. So kailangan ko muna yung LUB property na na-define na natin from unit 1 as our completeness axiom. Sumunod yung MCT. Tapos kasi ginamit ko yung LUB para sa kanya. Then yung MCT ang ginamit kong pang-prove ng NIP. So if you'll extrapolate the pattern, mukhang kakailanganin kayong NIP para ma-prove yung Bolzano Weierstrass. And let's take a look at how the module proved the Bolzano Weierstrass theorem. So ang assumptions sa Bolzano Weierstrass, bounded yung sequence. So let's consider a sequence that is bounded. All right? Sabi natin yung sequence AN. And since AN is a bounded sequence, then we can find a real number M who is larger or equal to the absolute value of all the terms in the sequence. So totoo itong inequality na yan. All right? Or we can say, or we can deduce from this inequality that AN is between negative M and positive M for all subscripts N. Right? So walang lalampas kay negative M at kay M, kaya siya bounded. Okay? Now we will divide the proof into two cases. Number one, yung madayang case. Kunwari, merong infinitely many repeating terms. Infinitely many yung mga ANs na pare-parehas yung value. Okay? And dahil infinitely many sila, pwede kong i-consider yung mga repeating terms na yon to be my subsequence. Alright? So, halimbawa, dito, infinitely many yung mga ANs na equal kay 1. So, i-harvest ko lang lahat ng mga 1s and that will form a new sequence. And then dahil i-preserve ko naman yung ordering, yung mga terms na yon will be my subsequence. Alright? Will form a subsequence kasi infinitely many sila. And then dahil constant subsequence yung nakuha ko, then we are sure that that subsequence will converge. And it will converge to the common value, right? So kung yung mga A sub n's lahat equal kay A, magko-converge sila obviously kay A. And then that proves Bolzano Weierstrass. Kapag infinitely many yung repeating terms. Okay? So I think yun yung medyo madayang part nung madayang case, yun yung madali. Now the more challenging one is when there are no or there exists no infinitely many repeating terms. So kunwari, posibleng nauulit lang isang real number, a finite number of times. So hindi natin kaya mag-form ng subsequence na constant. Okay? Now ganito yung gagawin ko. Ang spoiler ko kanina, gagamitin ko si NIP. So, dahil gusto kong gamitin si NIP, kailangan ko magkaroon ng mga nested intervals. So, unahin ko munang i-consider si I1. Si I1, i-define ko to be negative M to M. Hold on. Palitan ko yung kulay ng highlighter. Okay. So, negative M to M. Siya yung tatawagin kong I1. Okay? So, alam ko, yung sequence, lahat ng terms ng sequence nasa loob ng negative M to M. So basically, negative M to M contains infinitely many distinct terms of the sequence. All right? Kasi nga, walang infinitely many repeating terms. So merong infinitely many non-repeating or distinct terms in the sequence. At yon lahat ng element ng sequence ay laman ng interval negative m to m. Okay? So siya si I1. Kasi ko-construct ko si I2 this way. Si negative m to m, okay? So ito siya, negative m to m. Hatiin ko siya sa dalawang subintervals. So hatiin ko siya sa dalawang equal subintervals, or actually intervals of equal length. So kunin ko yung gitna nila si 0. Tapos i-consider ko na, okay, si I2 ay yung interval na naglalaman, interval between negative m to 0 or 0 to m, na naglalaman ng infinitely many distinct terms. Kasi nga, di ba sabi, alam natin na si negative m to m naglalaman ng infinitely many distinct terms of the sequence. So pag hinati ko si negative m to m, sure ako na at least isa sa kanilang dalawa, either negative m to 0 or 0 to m ang maglalaman ng infinitely many distinct repeating terms. Infinitely many distinct terms in the sequence. All right? Kasi hindi pwedeng parehas finite lang yung laman nila, kasi finite plus finite, sabi natin infinitely many yung distinct terms in the sequence, right? So alam ko at least isa sa kanila naglalaman ng infinitely many element nung sequence. Tapos kunwari, kung sino man yun yung tatawagin ko na I2. Kunwari, ito si I2. Kunwari lang. Or pwede na rin naman yung kabila. Pero yun yung usapan, siya yung magiging I2. So what we have right now is I1 is a superset of I2. All right? And then second, susunod. Ganun uli yung gagawin ko. So nandun na tayo kay I2. So kunwari si I2 ay 0 to m. Now, hatiin ko uli si I2 sa dalawang bahagi. 0 to m over 2 and then m over 2 until m. Right? Tapos pipiliin ko uli sa kanila sino sa kanilang dalawa yung naglalaman ng infinitely many distinct terms in the sequence. All right? Again, hindi pwedeng parehas finite lang yung laman nila, kasi finite plus finite magiging finite. Sabi natin infinitely many yung laman ni 0 to m. Right? So, pipiliin ko sa kanila to be I3 kung sino man yung naglalaman ng mahigit yung infinitely many distinct terms. And let's say, naka-achieve nun ay ito, si 0 to m over 2. Siya yung tatawagin kong I3. And obviously, by construction, si I3 ay subset ni I2. Ni I2. Alright? And then I will do this infinitely many number of times. So, gagawin ko yan. And then I am assured that I can do this infinitely many times kasi nga infinitely many yung distinct terms dun sa sequence. So, hindi ako mauubusan. Laging pag naghati ako ng interval, tuloy-tuloy ko silang hinati, laging may isa sa kanila na maglalaman ng infinitely many terms in the sequence. All right? So what we have now is a nested set of intervals, right? I1, I2, I3, and so on. So sabi ng nested interval property, then merong intersection. May non-empty intersection yung mga INs. So by NIP, the intersection of the INs and going from 1 to infinity is non-empty. All right? Actually, I can say something more about that. Paano natin kinonstruct yung mga I sub n's? Kinonstruct natin si I sub n so that yung haba ni I sub n ay kalahati nung haba ni I sub, tama ba? Ang haba ni I sub n ay doble ng haba ni I sub n plus 1. Tama ba sinabi ko? Ang haba ni I sub n ay doble ng haba ni I sub n plus 1. Mukhang mali yung nasa module, no? I sub n ay 1/2. Ang haba ni I sub n ay dapat doble ni I sub n plus 1. So I think this should be 2. Do you agree? Tama nga ba? Kasi si I1, ang haba niya ay 2m. Tapos si I2, ang haba niya ay m lamang. So ang haba ni I1 ay twice the haba ni I2. Right? So I'll just correct it later. But I think that should be it. Okay. Or in other words, we can say probably the length of I sub n is half the length of I sub n minus 1. I think this is what the lecture note tries to say. Okay. Ang haba ni I sub n ay kalahati ng haba ni I sub n minus 1. Kasi nga mas maliit yung subscript, mas mahaba yung interval, right? And then by design, we constructed the interval so that nangangalahati at every step yung haba nila. Okay? Now, let's take a look at it even further. So, tawagin nating yung interval in, tawagin nating Cn, Dn. All right? So, if we take the difference between Dn and Cn, let's try to get a formula for it. Ang haba ni Dn, ang difference ni Dn minus Cn ay equals sa length ni I sub n. So, yung absolute value bars ng isang interval ay yun yung haba ng interval, right? Ang haba niya ay kalahati ng haba ng previous sa kanya. Alright? That's what our observation gave us before. And then kung itutuloy ko yung process, makikita ko na yung haba ni I sub n minus 1 ay kalahati ng haba ni I sub n minus 2. Right? Essentially, what we get here is 1 over 2 squared, length of I sub n minus 2. And then, if we will extrapolate the pattern, parang ganito yung pattern. Kung ano yung subtrahend, yun yung exponent ni 2 dun sa ilalim. Right? Kasi paulit-ulit lang namang nangangalahati. So, ibig sabihin, pwede ko itong isulat as 1 over 2 cubed ng haba ni I sub n minus the subtrahend is equal to the exponent of 2. So I sub n minus 3. Right? And so on. Tapos kung gusto kong umabot kay I sub 1, right? Ano dapat yung denominator? 1 over what? What power of 2? Para ma-express ko yung haba ni Cn minus Dn as 1 over 2 to the power 2 to the something times the length of I sub n. Note that I sub 1 can be written as I sub what? I sub n minus, I sub 1 equals I sub n minus 1. Tama nga ba? Right? Pag sinimplify ko to magiging I1. So, ibig sabihin, ang haba nito ay 1 over 2 to the subtrahend to the n minus 1 times yung haba ni I1. Right? Pero ano nga, oops, sorry. Yeah. Delete ko na to para mabawasan yung nasa notes. Okay. Pero ano nga ba yung haba ni I1? Ang haba ni I1 ay, kasi si I1 ay negative m to m. So ang haba ni I1 ay 2m. This would be 2 to the n minus 1. So this guy will be m to the 2n to the minus 2. Alright? So paki-correct yung lecture notes. Dapat m over 2 to the n minus 2. Alright? But it's not a big deal because we want to take a look at what happens as n becomes larger, right? So we take the limit of this guy, pero habang lumalaki si n indefinitely, lumiliit indefinitely si n minus 2. So 2 to the indefinitely small number will go to, 2 to the indefinitely large number will become a large number. Constant m divided by a large number will tend to 0. Okay? Yung sequence m over 2 to the n minus 2 will converge to 0. Alright? So that means yung haba ng mga I sub n ay nagko-converge kay 0. Alright? And this is the addendum to the nested interval property na kapag ka nangyari na yung limit nung lengths ng mga interval ay naging equal kay 0, then isa lang yung laman ng intersection. Alright? Ibig sabihin, yung intersection nila, isa lang yung laman, si A. And actually, in the proof of the nested interval property, we discovered that A actually is the limit of the sequence. Okay? So nakita natin ngayon na, okay, pwede tayo makapag-design ng isang sequence, right? Or isang subsequence ni AN na magko-converge dito sa number A. Yung number A na yon ay yung intersection, yung nag-iisang intersection ng mga nested intervals, right? But how do we create such a sequence? So, ganito yung gagawin. Kasi kailangan, di ba, mapakita natin na may nag-exist na convergent subsequence. Meron na akong candidate ngayon para dun sa limit ng subsequence na yun, si A. Ngayon, ang problema na lamang, paano ko pipiliin si A sub n? Or paano ko i-design yung elements ng subsequence? Ganito yung mangyayari. Si A sub n, pipiliin ko to be any element of the original sequence that belongs to the first interval I1. Okay? And then, so, manggagaling siya kay I1. So, dun sa buong negative M to M, pipili ako dyan ng isang element ng sequence. Yun yung tatawagin kong A sub n minus 1. Okay? And then, dun sa I2, yun yung pipiliin kong pangalawang element ng subsequence. And then si I3, siya yung pipiliin kong pangtatlong element ng subsequence. And so on. But I need to do it so that N1 is smaller than N2, is smaller than N3, and so on. Which is guaranteed by the design that we gave to I sub n, to the I sub n's. Right? So, ganun natin pinipili. Nag-harvest ako kay I1 ng isang element ng sequence. And then kay I2, kukuha ko ng isang element ng isang term ng sequence, and so on. But I need to guarantee that laging palaki ng palaki yung mga original subscripts nila para makuha ko yung subsequence. So I am preserving the order in the original list kasi kailangan yun sa pagiging definition ng subsequence. All right? And then by the squeeze theorem, dahil yung mga A sub n sub k by choice or by design ay laging nasa pagitan ni Cn dn kasi yung A sub n sub k laging nasa loob ng interval in, alright? So by the squeeze theorem, dahil yung Cn nagko-converge kay A, yung Dn nagko-converge kay A by the nested interval property, then pwede natin gamitin yung squeeze theorem na sandwich si A sub nk, yung convergent subsequence, in between two sequences with a common limit. Therefore, that forces this subsequence to be convergent, and not just that, it will be convergent to the common limit nung dalawang nagsasandwich sa kanya. Right? So now we have constructed the convergent subsequence. Okay? So medyo constructive yung proof, and I hope you appreciate the intuitiveness. Sorry, not intuitiveness, but the creativity of the proof. So pwedeng ganito yung pagkaka-construct. Maraming mga proofs sa real analysis na ganito yung pagkakagawa by a very clever construction, right? Kaya medyo, I think, kaya mahirap yung advanced calculus o real analysis kasi may mga proofs na kailangan mo maging creative sa pagko-construct ng sequences or pagko-construct ng functions. Okay? But luckily for us, Bolzano and Weierstrass have this has developed this proof for us. Pero I hope you appreciate kung ano yung ibig sabihin ng proof, right? So is there any question about the proof? Okay, so if none, then I'll proceed to the next section, which will introduce to us another equivalent theorem to the completeness axiom, right? Ito naman ay tungkol sa mga Cauchy sequences, right? So ano yung mga Cauchy sequences? And that's in definition 2.8. So definition 2.8 tells us a sequence is Cauchy. So yung apelyido ni Cauchy ginagamit din natin as an adjective, right? So a sequence is Cauchy if for every epsilon greater than 0 there exists a starting subscript capital N such that whenever the subscripts little m and little n are greater than capital N, then the distance between AN and AM is less than epsilon. So can somebody interpret for me in layman's terms ano yung ibig sabihin ng pagiging Cauchy? Kailan nagiging Cauchy ang isang sequence? Anyone? Oh, habol plus pa to sa sa problem set 1. Based on this definition, you can think of epsilon to be a very small number. So yeah, how can you interpret, or how will you tell the story of Cauchy sequences to a layman? Ano yung interpretation ng pagiging Cauchy? Anyone? Any volunteer? Oh, come on guys, huwag na mahiya. Walang mag-volunteer. Tatawag na lang kaya ako. Kaya lang problema pag nagtawag ako, baka ma-pressure kayo, hindi na kayo umattend next time, no? So yeah. All right. So sige, free pass muna kayo. Siguro busy kayo pag-iisip ng problem set 1 pa. Okay. Ganito yung idea ng pagiging Cauchy. Yung pagiging Cauchy ng isang sequence, or Cauchy ang isang sequence kapag habang lumalaki yung subscripts. Alright? So kasi lagi ka nakakahanap ng big enough capital N na kapag lumampas ka kay capital N, yung so ibig sabihin yung subscript little n at little m ay mas malaki na kay n. Ibig sabihin yung an at saka am ay sobrang lapit na sa isa't isa. So meaning in layman's terms, ang isang sequence ay nagiging Cauchy kapag habang lumalaki yung mga subscripts, nagkukumpulan na yung mga terms ng sequence. Alright? So ibig sabihin we can impose any measure of closeness, say epsilon, however small that epsilon is, laging meron tayong mahanap na big enough capital N na kapag lumampas ka kay capital N, si AN at saka si AM ay sobrang lapit na. They are within epsilon distance from each other. So again, ang idea ng Cauchy sequence, yung mga terms dun sa sequence, palapit na ng palapit sa isa't isa habang lumalaki yung mga subscripts, right? So graphically, pwede nyo siyang imagine ganito. Ito yung real number line. Ito si A1, ito si A2, ito si A3, ito si A4. Okay? Pero pag lumalaki na yung subscript, ibig sabihin palapit na sila ng palapit sa isa't isa. So, yun na yung magiging itsura nila. So, ibig sabihin, in the tail end, nagkukumpulan or heavily concentrated yung elements ng sequence dun sa dulo. Alright? So, palapit sila ng palapit sa isa't isa. And you can do this for arbitrarily small epsilons. So, Cauchy, ibig sabihin, mga sequences sila na yung terms ay palapit ng palapit sa bawat isa habang palapit tayo ng palapit sa dulo. And you might say, parang wala siyang pinagkaiba dun sa pagiging definition ng convergent sequence. Alright? Kaya sabi natin, kapag ang isang sequence ay convergent, habang lumalaki yung subscript, palapit ka ng palapit sa constant number A, which is the limit of the sequence. Pero itong pagiging Cauchy, mas mabigat siya. Kasi hindi natin i-require lamang na palapit ng palapit siya sa isang constant. Pero dapat nagkukumpulan yung mga terms ng sequence. Palapit sila ng palapit sa isa't isa. Pero even saying it out loud, parang ngayon nasa isip ko pa rin, parang wala naman siyang pinagkaiba sa pagiging convergent. Right? Kasi pag sinabi natin convergent, habang lumalaki yung subscript, nagkukumpulan pa rin sila palapit ng palapit dun sa isang common limit A. Pero yung pagiging Cauchy, ang sinasabi niya lang, palapit siya ng palapit sa isa't isa. Yung mga terms and sequence palapit ng palapit sa isa't isa. Alright? So, an example, siguro bago tayo mag-prove ng mga bagay-bagay, siguro some concrete examples ng Cauchy sequences. Okay. The sequence 1 over n is Cauchy. So kahit ginagamit na adjective yung pagiging Cauchy, capital C pa rin yung gamit in honor of the French mathematician Louis Cauchy, right? Augustin Louis Cauchy. Yeah. Ito ay Cauchy kasi kung mapapansin nyo, ang first element niya ay 1, susunod ay 1/2, right? So ang nasa pagitan nila ay 1/2. And then ang susunod na element ay 1/3. Ang nasa pagitan nila ay what? 1/3 minus or 1/2 minus 1/3, and that's gonna be what? 1/6. And then 1/4. So ang difference between them ay 1/12. Tama ba? Sana tama yung arithmetic ko. Tapos 1/5. Ang difference nila ay 1/20. Right? And so on. So, and then the trend will continue. Etong sequence ng mga differences ay paliit ng paliit. So, ibig sabihin, palapit ng palapit yung mga elements ng sequences to each other as the subscripts increases, right? So, yun yung pagiging Cauchy niya. Kaya ba nating i-prove na siya ay Cauchy? I think so. Let's try. So, mag-PPA ako. So, we want to check ko lang kung may example dito. Yeah. Wala siyang binigay na example. So, let's see. Let's try this one. This easy one. 1/n is Cauchy, right? So, PA. Tingnan natin na, or here we want to find a little n, or sorry, a capital N, such that whenever little n and little m are larger than capital N, then a sub n minus a sub m, a sub m must be less than epsilon, right? Palapit ng palapit yung mga terms ng sequence sa isa't isa. Okay. Now, but what is 1/n and 1/m? They're both they are equal to 1/n and 1/m respectively. Okay. Tapos siguro without loss of generality. Yun yung ibig sabihin ng W log. Without loss of generality, I can assume that n is greater than or equal to little m, and they are both greater than or equal to capital N, right? So, ang ibig sabihin, kahit i-assume ko na si n ay mas malaki kay m, right? Hindi ko nalulose yung generality ng argument kasi yung proof kapag ka ang m ay mas malaki kay little n ay magfa-follow them. O kaya, edi pag-switchin ko sila ng places. So, gawin kong absolute value of 1/m minus 1/n, and the same proof will hold. So, kaya hindi ko nalulose yung generality ng statement. Okay. So, if this assumption is true, then ibig sabihin ang 1/n ay mas maliit kay 1/m, at yun ay silang dalawa ay mas maliit kay 1/capital N. Right? So remember, kailangan nating maghanap ng capital N such that for any given for some given epsilon, totoo itong inequality na to, right? But this guy is actually 1/n minus 1/m. Si 1/n ay mas maliit kay 1/n, right? Tapos nag-minus pa ako sa kanya ng isang positive number. So dahil itong number na to ay mas maliit kay 1/n, minusan ko pa siya ng isang positive number. So therefore, mas maliit ito kay 1/capital N. Right? Or actually, strict na itong inequality rito. Right? Do you agree with that? Si 1/n ay less than or equal kay 1/capital N. Pero, so ibig sabihin, pag si 1/n, binawasan natin by a positive number, say 1/m, strictly mas maliit na siya sa 1/n. And so we can impose, so now we can impose, so we want 1/capital N to be less than epsilon. And we can manipulate this and write it as 1/epsilon less than capital N. So pwede nating piliin si capital N to be any number that is greater than 1/epsilon, the existence of which is guaranteed by the Archimedean property, right? So yun yung binigay sa atin ng preliminary analysis. It gave us the choice of capital N para mapakita na Cauchy yung sequence 1/n. Is it okay if I leave the writing of the actual proof to you guys? Pabaliktad lang naman siya nung prelim analysis. So start case, a given epsilon greater than 0, then choose capital N to be any natural number greater than 1 over epsilon, the existence of which is guaranteed by the Archimedean principle. Then whenever little n is greater than or equal to capital M, greater than or equal to capital N, then the following inequalities will hold. Pabaliktad lang nung nandun sa prelim analysis ko. Actually, hindi nga pabaliktad, no? Compute nyo to, sabihin nyo equal siya dito, pero this guy is less than 1 over n, pero si 1 over n by choice is less than epsilon. So you're done. You will be able to show that a sub n minus a sub m has absolute value less than epsilon. Alright, so yun yung example o isang example ng isang Cauchy sequence. Now let's look at an example of a non-Cauchy sequence. One example is the sequence of logarithm of n. Right? This is not Cauchy. Okay. First element ng sequence ay log 1, pero ang log 1 ay 0. And then log 3, gawin na lang nating ln. So I think this will hold for any logarithmic base. So ln is not Cauchy. First element niya ay 0 because ln1 is 0, followed by ln1, ln2, ln3, ln4, and so on, right? So hindi siya Cauchy kasi hindi naglalapit-lapit yung mga elements ng sequence dun sa tail end. And then how to prove this? Well, we consider any n, right? Pili ako ng kahit anong little n. Then kahit, and here I can note that little n, however big. Kasi ang usapan sa pagiging Cauchy, pag malaki na yung subscript, palapit na ng palapit yung mga terms sa isa't isa. Pero dito sa ln na sequence, pumili ako ng kahit anong subscript n, however big it is. Then, kunin ko yung difference between a sub 2n at saka a sub n. Alright? Then what will happen is this is equal to ln of 2n minus ln of n. Mas malaki yung 2n kaysa kay n. So ibig sabihin yung ln 2n mas malaki kay ln n. So pwede natin kalimutan yung absolute value symbols. Positive yung makukuha natin. Alright? And then the idea here is what? The idea here is paano ko to masisimplify? Well, I can use properties of logarithms. I can write it as ln of 2n over n equal kay ln2. Alright? So ano napakita natin ngayon? Ang distansya sa pagitan ni a sub 2n at saka ni an, kahit ano pa si n, kahit n is equal to 10 million, kahit n equals 10 billion, ang pagitan niya at saka twice ng subscript niya ay laging ln2. So ibig sabihin, dun sa dulo ng list, dun sa tail end ng sequence, laging meron dalawang elements na ang distance nila mula sa isa't isa ay ln2. Hindi natin pwedeng gawing arbitrarily close si a sub 2n at saka si an mula sa isa't isa. Kasi constant yung nasa pagitan nilang dalawa. Kahit ano pa si n. Alright? Ang pagitan ni a sub 2n at saka ni an ay equal kay ln2. We cannot make them arbitrarily close to each other, no matter how big we choose the little n's to be. All right? So that means this is indeed not a Cauchy sequence. All right? Isa pang example ng hindi Cauchy na sequence ay medyo importante yung konsepto ng Cauchy. Kaya gusto kong ma-visualize nyo kung ano yung kailangan sa pagiging Cauchy, right? So, isa pang example ay, ano kaya example? Magbigay ako ng example ng Cauchy o hindi Cauchy. Sige. Gusto nyo ba homework material na example? Okay. yung sequence ng sum from k from 1 to n ng 1 over k squared ay Cauchy. Okay? Try natin yung prelim analysis. Tapos, kayo na yung bahala na isulat yung actual proof. Alright? So, analyze natin kung bakit to Cauchy. So again, if you cannot imagine what happens to or how the terms in the sequence look like, so pwede nyo ikunin muna yung first few elements. It is a sequence in n. So ang nababago ay si little n, hindi nababago si k as we increase the subscript, right? So dumadami lang yung terms dun sa summation. Okay? Now, if we look at a sub n minus a sub m, right? With, let's assume that n is greater than or equal to m, right? Prelim analysis yung ginagawa ko. Titingnan ko kung kaya ko ba silang gawing arbitrarily close to each other by just choosing ano dapat yung minimum value ni little n at saka ni little m. Alright? So, ito ay equal sa summation ng 1 over k squared, k going from 1 to n, minus sum k starting from 1 until little m ng 1 over k squared. So, parehas sila nag-start kay 1, so magka-cancel yung una nilang mga terms. Pero inassume ko na mas malaki si n, so pag pinag-subtract ko sila, dahil mas maliit si m, lahat ng mga terms na mas maliit kay little m, actually less than or equal to little m, ay maka-cancel out. So yung matitira natin in this difference would be the sum starting from k equals what? M plus 1 until little n ng 1 over k squared. Alright? So ito yung matitira. Tapos, meron akong trick na gagawin. K squared can be seen as k times k. Right? So, pagka pinaliit ko ng isa, pag pinaliit ko yung isa dun sa mga factors sa ilalim, I'll get a larger fraction. Right? So, ibig sabihin, ito ay pwede kong mas palakihin by decreasing one of the factors in the denominator. So, I'll still have summation from n plus 1 until n. Tapos gawin kong 1 over k times k plus 1. K minus 1. Kasi nga pala gusto kong mas palakihin yung fraction, so paliitin ko yung isang factor. So definitely ito ay mas maliit kesa dito, making the fraction or this fraction larger than this fraction. Okay? And then this guy ay pwede kong isulat as the sum of, pwede kayo mag-partial fraction decomposition, m plus 1 until n, ng 1 over k minus 1 minus 1 over k. K goes from 1 to m plus 1. So, kung natatandaan niyo sa 38, yung nung nag-discuss kayo ng series, partial fraction decomposition. Okay? And then, if I will spell out this summation, this will look like 1 over, plug in m plus 1 for this k. So, we'll have 1 over m minus, plug in m plus 1. So, we'll get 1 over m plus 1 plus, let's plug in m plus 2. So I'll have k is m plus 2. So I'll have m plus 2 minus 1. So I'm going to get m plus 1 minus 1 over m plus 2, right? Tapos, kapag ka si k ay m plus 3 na, I'll have 1 over m plus 2 minus 1 over m plus 3, and so on, until we reach the upper subscript k equals n. So ito ay magiging 1 over n minus 1 minus 1 over n. Okay? And then telescoping series siya kasi yung mga middle terms ay magka-cancel lahat. Alright? So kung tandaan niyo yung telescoping series, right? So, yung negative m plus 1, makakancel ng m plus 1, negative m plus 2, makakancel nito. Ito, makakancel ng susunod. Tapos ito, makakancel nung before. Magko-collapse yung nasa gitna nung summation. Matitira lang yung yung start nung sequence, yung start nitong mahabang summation at saka yung end. Parang dito yung viewing portion ng telescope, tapos ito naman yung object na gusto mong i-observe, right? So essentially, this guy is just 1 over m minus 1 over n. And what do we know about 1 over m and 1 over n? We want to choose capital N so that, remember, so we want n and m to be greater than or equal to capital N. Now, kung si n ay mas maliit kaysa kay capital N, ibig sabihin this guy is smaller than 1 over n. 1 over capital N. Tapos, kapag kayong mas maliit kay 1 over capital N, minusan ko pa ng isang positive number, mas lalong liliit yung difference kaysa kay 1 over capital N. And then to force the issue that it is Cauchy, we want to impose that 1 over n or 1 over capital N to be less than epsilon. So we will choose capital N to be a natural number such that 1 over epsilon is smaller than capital N, the existence of which is guaranteed by the Archimedean principle. All right? So with that, napakita natin na yung summation ng 1 over yung sequence comprised of terms of partial sums of 1 over k squared is Cauchy. All right? Any questions with that? Or masyado bang komplikado? Paramdam lang kayo, guys. So I want you to try this. Baka lumabas sa homework or sa problem set. Sequence of 1 over k going from 1 to n, sequence taken over n, is not Cauchy. Okay? So try nyo i-prove na hindi siya Cauchy. Ibig sabihin, makakahanap kayo ng dalawang elements na kahit malaki yung subscripts nila, hindi natin magawang palapitan sila sa isa't isa. Alright? Proving that it is not Cauchy. Alright, please try that. So let's go back to the lecture notes, all right? Okay, now here are some preliminary results before we go to the actual Cauchy criteria, Cauchy convergence criterion, which is basically our target for today, na major theorem, aside from the Bolzano Weierstrass theorem. Okay, so one result is that every convergent sequence is Cauchy. Okay? Kasi kung mapapansin nyo, magkamukha yung definition ng convergence at saka Cauchy. Everything is the same except that a sub m is replaced by the limit of the sequence. All right? So, ang sinasabi ng Theorem 2.11, kapag ka pala convergent yung sequence, automatic Cauchy na siya. Which makes sense kasi pag sinabi natin convergent, palapit sila ng palapit to a common value. So kung palapit sila ng palapit to a common value, dapat magsiksikan sila malapit dun sa limit ng sequence. At dahil magsisiksikan na sila dun sa dulo, dun sa malapit sa limit ng sequence, ibig sabihin mafo-force yung mga elements ng sequence na nandun sa dulo ng listahan to be very, very close to each other because all of them must be very, very close to the limit of the sequence. All right? Kaya parang madaling tanggapin intuitively na kapag ka-convergent, automatic na siya ay Cauchy. All right? And here's the proof. So assumption, we should have a convergent sequence. So let's take one. Let's suppose the sequence AN converges to A. And then gusto nating ipakita na siya ay Cauchy. Again, gusto nating mapakita na true tong inequality na to. Right? Pero gusto kong mag-start. Ano ba yung alam ko sa pagiging convergent? Sa pagiging convergent, alam natin na for any epsilon greater than 0, may lower subscript tayong mahanap such that starting from that subscript capital N, yung a sub little n ay magiging within epsilon over 2 units away from a, which is the limit. Okay? So ginamit ko lang dito definition ng convergence. And then again, our goal is to show that with the same choice of capital N, dapat yung a sub n minus a sub m ay mas maliit na kay epsilon, provided si n at saka si capital N ay mas malaki na kaysa kay capital, ay mas malaki na kay capital N. Okay? And that's easy. So I'm gonna start with this. Kaya doon ko siya sinimulan. Dahil gusto ko sila ay ma-compare kay limit A. Kasi meron lamang akong statement about the limit A. Ito, walang limit A, hindi involved si limit na equal kay A. So, kailangan ko mag-insert ng something. Alright? So, gagawin ko, mag-add and subtract ako ng A. Right? So, ito yung gusto natin ipakita na less than epsilon. Pero so far, ang alam natin, less than epsilon over 2 yung an minus a. So, kailangan magkaroon ng mga a's. Right? So, kaya ginawa ko, nag-add subtract ako. Tapos, pwede kong i-rearrange yung terms so that this will become a sub n minus a plus a minus a sub m. Right? And then, gagamit ako ng triangle inequality. Pwede kong i-split itong absolute value ng sum into a sum of absolute values, and I'll get a larger one. So, kinuha ko yung first two parts. Ito sila, inside an absolute value. And then, kukunin ko to, absolute value of a minus am, tapos mag-factor out ako ng negative 1. So, maging am minus a. Pero ang absolute value ni negative 1 ay positive 1. So, ito lang yung matitira. Okay? So, kailangan ko pala ditong sabihin na si little n at saka little m ay mas malaki kay capital M. Kasi kung si little m at saka little n ay mas malaki kay capital N, then yung an minus a ay magiging mas maliit kay epsilon over 2 by the assumption that a is the limit of the sequence. And in a similar manner, dahil si little m ay mas malaki kay capital N, etong statement na to, mangyayari rin kapag si little n pinalitan ko ng little m. So absolute value of a sub little m minus a will also be less than epsilon over 2. Alright? So ito ay mas maliit kay epsilon over 2. Ito mas maliit din kay epsilon over 2. So yung sum nila mas maliit dun sa sum ng mga epsilon over 2's, which is equal to epsilon, which ends our proof. Okay? So this tells us na lahat ng convergent sequence necessarily dapat ay Cauchy. And the next question is, what happens for the converse? Lahat kaya ng Cauchy sequence ay convergent? And the answer is affirmative. Lahat ng Cauchy sequence ay convergent din. And that's what we will prove, and that is what is called the Cauchy convergence criterion, which is Theorem 2.12 here. But in order for us to prove Theorem 2.12, i-prove muna natin yung Lemma 2.1. Si Lemma 2.1, ang sinasabi niya lahat ng Cauchy sequences dapat ay bounded. Right? Tingnan natin kung bakit siya dapat bounded. Intuitively, kung ipa-plot natin yung mga terms ng isang Cauchy sequence, dapat, pwedeng ganito siya sa simula, pero dapat habang lumalaki yung subscript, dapat nagkukumpulan sila sa isa't isa. So dahil nagkukumpulan na siya sa isa't isa, dapat at some point, mababound natin siya. Hindi siya lalampas sa isang number. Okay? Kasi pag lumampas siya sa isang number, posible na yung dalawang terms ng sequence na parehas malaki yung subscript ay magkakaroon ng mahabang difference or malaking difference. Okay? Now, here's the formal proof bakit dapat totoo na ang mga Cauchy sequence ay bounded. Well, dahil ang assumption dito, meron kang Cauchy sequence. So kahit nagbigay ka ng kahit anong epsilon, say epsilon equals 1, then may mahanap tayong lower bound dun sa mga subscripts ng sequence such that kapag ka lumalaki na yung subscripts that they are larger than capital N, then A sub N minus A sub M will have absolute difference less than 1. Kaya kung pumili ng starting subscript na pagkatapos ng starting subscript na yon, ang distance between AN and AM ay mas maliit sa 1. Okay? Now, it follows that para sa lahat ng N na mas malaki kay capital N, totoo itong inequality na to. Alright? So, papalitan ko lang si little m by capital N. Alright? Kasi kung mapapansin nyo, ito ay greater than or equal to. Right? So, pwedeng si little m maging equal kay capital N. So, ibig sabihin, specifically, A sub N minus AN would be less than 1. Ibig sabihin, yung distance sa pagitan ni A sub little n, kahit anong A sub little n, si n ay arbitrarily malaking number, mas malaki siya basta kay capital N. Si A sub n ay fixed by our choice of epsilon equal to 1, and distance nila mula sa isa't isa ay less than 1. Tapos gagamit ako dito ng triangle inequality, absolute value of AN plus absolute value of A sub big N ay less than 1. And so we will get this guy. Bakit nakuha yung A sub N plus 1? Okay. Kasi nga mula dito ay A sub little n ay mas maliit kay 1 minus A sub n. Pero dahil ito ay positive, nagma-minus ako ng isang positive number, for sure, mas maliit yon sa 1 plus absolute value ni 1 over n. Alright? Kaya natin, strict pala yung inequality rito. Kaya ako nakuha ito. Alright? So, ibig sabihin, lahat ng A sub n ay mas maliit kaysa kay A sub n plus 1. So, ibig sabihin, eventually, nagiging bounded yung mga terms ng sequence. Simula kay A sub n, pag yung subscript ay mas malaki na kay capital N, yung terms ng sequence ay nagiging bounded above by the absolute value of A sub n plus 1. So, ang problema na lang natin ay yung mga nauuna, ano yung man nangyayari or ano yung pang-bound natin dun sa mga A sub n na si little n ay mas maliit kay capital N. Kasi ang ibig sabihin nito, eventually nagiging bounded siya. Pero ang gusto nating ipakita, bounded. So ibig sabihin, kahit ano pa si n, ang A sub n dapat mas maliit kay m. Okay? Pero dito, yung A sub n ay less than this value is only true whenever little n is greater than or equal to capital N. Hindi natin alam kung ano yung nangyayari kapag si little n ay mas maliit kaysa kay capital N. But that's easy kasi meron lang tayong finite number of cases na hindi covered ng statement na to. Namely, sila si A sub 1, A sub 2, hanggang A sub n minus 1. Sila yung mga hindi natin sure kung mas maliit kaysa kay A sub n plus 1. So kaya para mahanap yung upper bound, dahil hindi ako sure kung sino yung pinakamalaki sa kanila, kunin ko yung absolute value ni A sub 1, absolute value ni A sub 2, hanggang absolute value ni A sub n minus 1. Tapos kukunin ko yung pinakamalaki among these guys and A sub n plus 1. At yun yung tatawagin kong m. So kung pipiliin ko si m in that way, sure na ako na si A sub little n ay ang absolute value niya ay mas maliit kaysa sa capital M for all n, however big or small that little n is. Okay, so by design or by construction ni capital M. And that proves na lahat ng Cauchy sequence ay bounded. All right? Now, here's the main dish for today, the Cauchy convergence criterion. or simply the Cauchy criterion. Pero usually na-abbreviate ko siya as CCC, Cauchy Convergence Criterion. Ang sabi ni Cauchy Convergence Criterion, a sequence in R converges if and only if it is a Cauchy sequence. So pwede palang gawin nating definition ng convergence ay yung pagiging Cauchy. Kasi if and only if siya. Being Cauchy is necessary and sufficient for a sequence in R to be convergent. At yun yung sinasabi ng Cauchy convergence criterion. Right? Quickly, let's do the proof, and then probably at the end, I'll say a couple of words about the Cauchy, the implication of the Cauchy convergence criterion. Okay. Now, yung forward, meaning kung siya ay sequence in R na convergent, implying siya ay Cauchy, na-prove na natin yon. That is essentially Theorem 2.11. Okay. So, ang kailangan na lang nating i-prove ay yung converse ng Theorem 2.11. Meaning, we will assume that we have a Cauchy sequence and we want to show that that Cauchy sequence is convergent. Okay? Kasi na-prove na natin na kapag ka-convergent ay Cauchy. So, ang kulang na lang ay kapag ka siya ay Cauchy, automatic siya ay convergent. Alright? So, for the proof, we will assume that we have a Cauchy sequence. Right? Then, by lemma 2.1, bounded yung sequence na yun. Kasi lahat nga ng Cauchy sequence ay bounded. Then, by the Bolzano Weierstrass theorem, maybe ginamit ng iba yung reference nung module. Baka kaya sadyang Bolzano yung tawag niya. But I'll stick to Bolzano. Mas gusto ko yung Bolzano kaysa sa Bolzano. So, by the Bolzano Weierstrass theorem, kapag ka meron kang bounded sequence, then meron siyang convergent subsequence. Alright? Now, tawagin natin yung convergent subsequence na yon na A sub nk. So, ito yung convergent subsequence ng Cauchy sequence natin. And then, let's say the limit of that subsequence is equal to A. And since the limit of the subsequence is A, this is our prime suspect para maging limit ng full sequence. Alright? So, let's retrace our steps. Consider ako ng Cauchy sequence. Sabi nung lemma, bounded lahat ng Cauchy sequence. So, this guy must be bounded. Tapos sabi ng Bolzano Weierstrass theorem, kapag ka meron kang bounded sequence, meron siyang convergent subsequence. So, suppose si A sub nk yung convergent subsequence na yon, and further, nagko-converge siya kay A. Dahil gusto nating ipakita na yung sequence ay convergent, so ibig sabihin kung yung subsequence niya ay nagko-converge kay A, para hindi siya maging divergent, dapat yung limit ng full sequence ay equal din kay A. And that's what we want to prove for the rest of the proof. Okay. So moving on. All right. Okay, gusto mo ipakita na limit niya ay si A. Then alam ko na siya ay Cauchy. So I'll go by the definition of pagiging Cauchy. So since AN is Cauchy, then given any epsilon greater than 0, we can choose a capital N such that si AN at saka si AM, whenever little m and little m are greater than capital M, yung distance between them can be arbitrarily small, say epsilon over 2 small. Okay? And then, dahil ito ay totoo, okay, sa lahat ng subscripts N and M, such that basta mas malaki siya kay capital N, pwede akong pumili doon kay ng isang subscript N sub K na mas malaki kay capital N. So, ibig sabihin, pipili ako ng isang element doon sa subsequence na yung subscript niya na N sub K ay mas malaki kay capital N. Dahil yung pagiging Cauchy nag-a-apply doon sa buong sequence. Pag kumuha ko ng A sub nk doon sa subsequence and it still happened that N sub K is larger than capital N, then yung inequality dito sa pagiging Cauchy ay mag-hold pa rin. Alright? Pero bonus na alam natin yung A sub N, yung A sub nk ay nagko-converge kay A. So, totoo rin tong inequality na to. So, we have this inequality and we'll have the inequality that A sub n sub k minus an is also less than epsilon over 2 from pagiging Cauchy, right? Kasi again, si n sub k ay pinili ko to be larger than small n, smaller is larger than capital N. So ibig sabihin, si a sub n sub k ay within epsilon over 2 units away mula kay a sub n, mula sa pagiging Cauchy. Ito naman ay mula dun sa pagiging convergent ng subsequence. Alright? So pwede kong palitin yung distance ni a sub nk mula kay a up to epsilon over 2. So these are the two working inequalities that we have involving a sub nk, a, and a sub n na gusto kong paghugutan nung inequality na an minus a less than epsilon. And true enough, if you look at this, ito yung kailangan nating mapakita to be less than epsilon para ma-prove na si an ay nagko-converge kay a, right? Manipulate ko lang to, mag-add and subtract ako ng a sub nk because the two ingredients I have both involve a sub nk. So, by hook or by crook, dapat ako magkaroon ng a sub nk dun sa absolute value. And so I will add and subtract a sub nk. That's why it pop out of the blue here. Okay. Tapos triangle inequality uli ako so that I'll have these two guys together and these two guys together inside an absolute value. The reason why I want to do that, because here I know that a sub n minus a sub nk is smaller than epsilon over 2 by the pagiging Cauchy nung sequence a sub n. Right? And then this guy is less than epsilon over 2 dahil sa pagiging convergent nung subsequence papunta kay a. So these two guys are both less than epsilon over 2, so their sum should be less than epsilon. And that completes the proof. Na yung a sub n minus a ay less than epsilon for any choice of epsilon, provided little n is greater than or equal to capital N. Okay? And that ends the proof. And you see, ito pa pala yung kasama dun sa chain of results that we have. So, na-prove natin si Bolzano Weierstrass gamit yung NIP. Tama ba? NIP yung ginamit natin sa kanya. So, mula naman kay Bolzano, na-prove naman natin yung Cauchy convergence criterion. So, and again, this is another equivalent form of the LUB property because you can show, or actually, I think it can be done that the Cauchy convergence criterion be used exclusively in order to prove the LUB property. Actually, sa masters, isa to sa pinaghandaan kong questions nung compre exam dun sa master, nung nagma-masters ako sa UPLB, na malamang ipapaprove yung equivalence nung completeness theorems. So merong siyam or 12 equivalent statements. Pinaghandaan ko na gumawa ng diagram para ma-prove na lahat sila ay equivalent sa isa't isa. So gumawa ako dun ng cycle. Ano yung ipoprove ko gamit sino para ma-complete yung circle, right? O yung cycle ng equivalencies. And I guess we have a good number of equivalent statements to the completeness axiom, right? Oh, but by the way, the Cauchy convergence criterion will only work for sequences of real numbers. Kasi nga gumamit tayo dito ng Bolzano. Si Bolzano ay equivalent sa LUB property. Siya ay equivalent sa completeness axioms. So kapag ka hindi complete yung set, hindi mag-hold yung Cauchy convergence criterion. So kung gusto nyo maghanap ng Cauchy sequence na hindi nagko-converge, hindi nyo kayang kumuha sa R kasi si R ay complete. So pwede kayong kumuha sa mga sets na hindi complete, posible makahanap kayo ng Cauchy sequence pero hindi nagko-converge. Okay? But insofar as the set of real numbers are concerned, gina-guarantee ng Cauchy convergence criterion o CCC na kapag ka siya ay Cauchy, automatically siya ay convergent and vice versa. Actually, we can use Theorem 2.12 as our alternative definition sa pagiging convergent. Na pwede nating i-define yung convergence sa pagiging Cauchy. Okay? But I guess it's nicer to have this result. So kung mahirap na ipakita na convergent ang isang sequence, pakita nyo na lang na yung sequence ay Cauchy. Kasi ang problema sa pag-prove na siya ay convergent, by definition, kailangan yung humanap kung ano yung limit ng sequence. Kung hindi nyo alam or mahirap computein yung limit ng sequence, tapos hindi nyo naman siya kailangan, pakita nyo na lang na siya ay Cauchy para makonclude na siya ay convergent. Given, dapat, yun pala muna, meron kang sequence of real numbers or yung sequence may under ni R. Okay? All right, so I think that's a good place to stop. Any questions, guys, or any comments? Di pa rin kayo nagpaparamdam, no? So ano kayang pwede kong gawin para mapilitan kayo na magparamdam habang nagdi-discussion? Medyo bibigyan ko kayo ng free pass ngayon kasi busy kayo sa problem set 1.1. Sorry, sa problem set 1. So, okay. Are there questions? So, after nito, isa na lang yung kailangan nating i-state, yung Heine-Borel theorem. And I guess definitely will be done with Unit 2 on Thursday. So, ipupush na natin yung problem set 2 next week. All right. So, any other questions, concerns? Okay, so kung wala na, thank you all for joining me today. So enjoy the rest of the night. And then let's see each other again on Thursday. All right? Bye, everyone. Don't forget pala, deadline ng problem set ay bukas. Deadline na, meron tayong homework number 4, available na sa Canvas, pero ang deadline ay October 29, hindi November 29. All right? Edit ko siya later tonight. Okay. All right, so bye, everyone. See you on Thursday.
Thank you, sir.
Yep, you're welcome.
Thank you po, sir.
Uh-huh.